So this is the last video in nuclear physics about the topic nuclear physics, and especially about binding energy. So the topic of binding energy and the problems that you might find in the MCAT about that. And so they are very simple problems. The mathematics is not that hard. So you remember the equation of Einstein, E equals mc squared, because it's the most famous equation. That equation here just says that mass is a form of energy, except that when you go from mass here, so here you go from kilogram, for example, to joules, so this is the unit of energy. You have other unit of energy and other unit of mass, but let's say you go from kilogram to joules, then you need a conversion factor, c squared. So this is a conversion factor. But c is the speed of light, so it's going to be a very, very, very big number. So it means if during a nuclear reaction, a little bit of mass is lost, that will translate into a huge amount of energy. So in nuclear reaction, you're going to release 1,000,000 times more energy that you are releasing in a TNT or a chemical reaction. Okay, so c is the speed of light, and it's going to be a big number. Okay, so mass can be converted to energy, and that happens in nuclear reaction. So for example, fusion. So fusion can happen, does happen in stars. Okay, so in stars, because you have, and that can only happen if you have very, very high temperature and high pressure. So protons can be close enough that the strong nuclear force takes over. They fuse together, okay, and energy is released. A huge amount of energy is released. That will be the energy that we harvest from the sun. And we kind of do the same thing when we build a nuclear weapon, for example, based on fusion. So you use fission to increase temperature and pressure, and then you're going to fuse hydrogen into helium, except it's going to be different isotopes of hydrogen that you fuse, but the idea is the same. So where that energy comes from, it comes from the mass defect. So if you find the mass here of helium and you compare to the mass of the 4 protons, it's going to be less, right? So you are losing some mass here. That mass will be pure energy. Okay, so how are you going to find that energy here in that fusion reaction? So a reaction, nuclear fusion reaction, only happens because you are releasing energy. So the nuclei that you get, the nucleus that you get will be more stable. So that energy here that will be released will be the mass defect. Okay, so if this is a mass M2, and that will be a mass M1, so we're going to have M2 minus M1 times c squared. So this is called a mass defect. Okay, and you use Einstein equation. Now, if you want to have that energy released in the unit MeV, for example, so it's typical for nuclear reaction. So then that mass here, you can use for the mass, you can use a different unit, which is the atomic mass unit. Okay, and c squared will be 932. Okay, MeV per atomic mass unit. So the atomic mass unit is the mass of 1 proton or mass of 1 neutron. So this is the idea of a nuclear reaction, is that fusion, in the case of fusion, you're going to have energy released because there was a mass defect. Okay, the mass here, okay, will be lower than this mass there. So the loss of mass will be energy. Okay, so the energy will be in the form of kinetic energy of neutrons, if neutrons are emitted, or whatever is emitted, or whatever particles will be emitted. So it's the same idea when you have fission. So with a fission, you have a nuclear power plant inside a nuclear power plant, or inside an atomic bomb, for example, or it can happen also in nature. You're going to shoot a neutron at uranium-235. It's going to split into different product nuclei. It's a split apart, and it's going to release energy. Okay, that you can find also finding the mass defect. Okay, here's another example here. In an atomic bomb, for example, you are fusing atomic bomb. It doesn't have to be a nuclear weapon. It could be, for example, fusion that you are trying to do on Earth. For example, in the tokamak, they are trying to fuse hydrogen into helium. So the way you will do that, you will take an isotope of hydrogen, which is deuterium. You combine that with tritium. You need very high temperature and high pressure. And the product here will be helium and a neutron. And that neutron, most of the energy released will be in the kinetic energy of neutron. Some of it will be in the kinetic energy of the helium. Now, if you find the mass of the product here, that will be the mass. The unit is atomic mass, atomic unit mass. Okay, you see that mass here, the mass of this is less than the mass of those. Okay, so it's a little bit less. That energy, that mass is energy, and you find it using equation. The equation of Einstein, delta E equals delta mc square. Okay, and energy, usually you use the energy EV, the unit EV. Okay, so likewise, when you have nucleus, okay, you have to glue all those nucleons together. All those nucleons together have to be forced together, have to be squeezed, because you have high temperature and high pressure, say in a star, and then a strong nuclear force will take over, okay, and in that case, some of the mass will be lost. Okay, so the mass of the nucleus will be less than the mass of the total nucleons. Okay, so you take the mass of all the nucleons together, you can have more mass that what you get here, the nucleus. So that mass defect, okay, that mass defect is the nuclear binding energy that you can find with this equation. So it's like all those nuclei, they have a binding energy, which is called, it's like potential energy, okay? So when you put them together here to make nitrogen, the mass of nitrogen here will be less than the mass, the sum of all the masses here that you add them together. It will be less because you need that binding energy, that negative potential energy, okay? Because you have the glue, okay? The energy is in that negative binding and that negative potential energy. So it's like a glue. Now, as you increase the size of the nuclei, then you need to increase the number of protons to increase the binding energy, okay? Because you need to overcome the positive potential energy that you have between the protons, okay? They repel each other. So it's like a fight between them. So more and more neutrons have to be added. And then you get to uranium-238, which when a nucleus is unstable, okay, it can break apart. There is a probability that it will break apart. And anything larger than uranium-238 will be not stable. So anyway, let's take an example to make it more clear. Here, you have a nice example there. Okay, so that means the mass here of the nucleus will be always smaller than the sum of all the masses of the nucleons. So this is called the mass defect, which is turning into energy using this equation found by Einstein. And again, if this is in joule, that will be in kilogram, and that will be the speed of light. If instead you are using EV, MeV, so then the mass will be in atomic mass unit, okay, AMU, and then C is just the factor, which is 932. Okay, so let's try to do this one. They talk about argon-40. So argon-40 is a noble gas. So it's very, very, very stable. And it's used in medicine because you can make a plasma with that gas, and you use it for cauterization, okay, to stop bleeding. For example, when there is a surgery in the intestines, for example, or guts, inside the guts, right? You can do some cauterization or to stop bleeding when there is a surgery in dermatology on the skin. So you can use that very hot plasma. So you use argon, you use a very high voltage, so the gas get ionized, and you use that plasma for coagulation, right? So it has application. So for the MCAT, they always try to find some application in the medical field, something that makes sense. Not always, but most of the time. Okay, so let's try to do this one. Of course, you can stop the video. You should stop the video and try to do it. Okay, so binding energy, they give you the definition, is the energy required to separate a nucleus into its individual protons and neutrons. So you are filling the gap, right? So a nucleus has negative energy. So if you want to break it apart, you need to give it energy. So it tells you how strongly the nucleus is held together. Okay, so it's argon is very stable. So we want to find the binding energy of argon-40. So we have the mass of a proton is 1.0073 atomic mass unit. The mass of a neutron is 1.0087 atomic mass unit. And about, atomic mass unit is about 1.6 and 10 to the negative 27. About. So anyway, use those units here. Okay. So, and this is the mass of argon. So if you take all the protons here, and then you have all the neutrons, and if there was a way to combine them together into one nucleus, so the nucleus of argon, so now they are bound together, okay, because of that glue. So it's a negative potential energy. So then you will release some mass, and that mass will be energy. So you need to find the mass before, the mass after, and then you use that equation here. Okay, so argon, I don't know where I'm going to write now. I can erase this. So if you take argon here, and you do have access to the periodic table. So argon, it has 40 nucleons. Okay, so 40 nucleons. So that will be the mass number. 18 is the atomic number, so the number of protons. So the mass before here of all the nucleons, you're going to have 18 protons. So 18 times 0.073 plus 22, 1.0087. Okay, so you can compute that, and usually the computation will be easier. Okay, and you get 40.323 AMU. So that's before, okay, when they are not bound together. Now, once they are bound together, if you find the mass, it's going to be, it's given here, so 39.91, 39.9132. Okay, and if you don't have to keep all the decimals, so it should be about 0.5 atomic mass unit. So that will be your mass defect. Once you have that, you can say that the binding energy, okay, so how much energy was released? It's going to be equals to delta M times C squared. And if you want the energy in MeV, so that's going to be 0.4 times C squared here. It's given, so 932. And that's going to be MeV. And that will be the answer. So you divide by 4. And if you divide by 4, about 4, not divide by 4, you multiply your 4, divide by 10, and you get about something like this. As you can use the multiple choices, right? So it's going to be about 382 MeV. Okay, so that's about binding energy. So any nuclear reaction, so that could happen in a star, for example, during nuclear synthesis. You take all those nucleons together, you're going to bind them together. So energy has to be released, and it comes from the mass loss. Okay, so let's do the next one here. Okay, so they tell you a story. So this is also a nuclear reaction. So it means if the nuclear reaction happens, you're going to have released energy because there will be a difference in mass between the product here and the reactant. There is a loss of mass. And what's going on here? So you have boron, and boron is a neutron capture. So this kind of reaction here, it's a capture. So it's a capture of a neutron. And you get lithium and helium. So the energy release will be mostly probably in the kinetic energy of the alpha particle there. So do you use that in medicine? One example will be there is some trial where if you have a cancer tumor, you can inject inside the tumor boron, and you can bombard with neutron very, very carefully, of course, and the energy released will kill the tumor. But it's an experimental stage, I think. So that's an example. So anyway, you can pause the video and try to do it. It's again, once you understand how it works, it's not that hard. So again, it's a neutron capture. So you have one neutron here, and the neutron, the mass is given. And then you have boron. So boron is also given, so 10.0129. And then you have lithium, which is 7.0160. And then you have helium, which is 4.0026. Okay, so you can find the mass defect. So you add that together, you add this together, and you subtract this mass here from that mass there. Okay, so if this is M1 and this is M2, okay, you need to find M1 minus M2. So you can pause the video and do it, and you should find the mass defect, 0.003. Okay, so that will be the energy released per equation, right? So it's going to be 0.003 times 932 MeV. Okay, because again, delta E equals delta M C square. So if this is 932, the unit here will be AM, atomic mass unit, and that will be in MeV. Okay, and you can try do it, and you should find about 2.8 MeV. And of course, the questions will be, I mean, the numbers will be easier to deal with. It's not that hard, but takes steps. Okay, so let's do, almost done. Let's do the next one here. So that's an interesting process. And so this is not happening in stars, but this is what we try to do on Earth. Or we are doing it on Earth in a nuclear weapon. But we are trying also to do it under control in, for example, tokamak. So anyway, this is a fission reaction. So you have one isotope of hydrogen here, which is deuterium, because it has two neutrons, one neutron and one proton, two neutrons and one proton. That will be tritium. High temperature, high pressure, you combine them together, you get helium and a neutron. So most of the energy released will be in the kinetic energy of the neutron, some of it in the kinetic energy of the alpha particle. And that energy comes from the mass defect. And that's what they want you to compute. Okay. So this is given. So that will be deuterium. Deuterium, the mass is given. And then here you have tritium is also given. Okay, so the mass of helium is an alpha particle is also given. And then you have a mass of a neutron. And you can find the mass defect. Okay, so you add them together, and then you do the subtraction, and you will get something like 0.0188 atomic mass unit, right? So to find the energy released, you just have to multiply that mass defect times 932. Okay, and you find 17.6 MeV. Okay, that's all there is to it. It's not too complicated. Right? So you can have fusion or fission, doesn't matter. You are still releasing energy because energy is lost. Okay, this is the example of fusion. And if you go back to my slide here, okay, when you put 26 protons and 30 neutrons together, for example, you're going to get iron 56, which is very stable. But if you find the mass of the nucleus here and the mass of all the nucleons added together, there will be a mass defect. And that mass defect is what we call the binding energy, right? So iron has a very large binding energy. I used to have a very nice slide, but okay. Yeah. So any nucleus will have a negative potential energy, so it has a binding energy that comes from the loss of mass, the mass defect. Okay, so here you have some mass of a neutron, mass of a proton, So neutron mass is a little bit larger than a neutron. Okay. So here you have the mass in AMU. So that will be atomic mass units. It's just a unit of mass. Okay, it's another unit of mass. Okay.